Recording and share screen. So, first things first is to finish this chapter. This chapter is the one we need in order to finish up the last lab. And this is kind of going to relate everything we've kind of done up till now, like with our equilibrium constants, into our thermodynamics. This is where we kind of really come full circle again. So remember that that we first talked about kinetics. Kinetics is the rate at which a reaction goes. Then we moved on to equilibrium, where you're looking at the speed of the forward reaction versus the speed of the reverse reaction. That's going to make our equilibrium. And then once we get a point where the concentrations level out, they stop effectively changing, we say it's at equilibrium. We looked at that, and then we said, okay, now can we look at the equilibrium reactions of some special cases? The special cases being acids, bases, and solids dissolving. Finally, we're going to relate this equilibrium to what is the likelihood of this reaction proceeding forward or reverse. Remember that when we were talking about equilibrium in chapter 15, we said that Q is the reaction quotient at any given time. But over time, Q will shift to achieve K. Q will shift in order to achieve K. K is the equilibrium quotient only at a specific time where we're at equilibrium. So as Q is shifting towards K, delta G non-standard is going to shift towards 0. Because when delta G is 0, the reaction is at equilibrium. It's no longer spontaneous to go forwards. It's no longer spontaneous to go backwards. And so that's what we're relating, that we can say that from a relationship, previous relationship, that what? Come on. Okay. We could say that previous relationship, that delta G non-standard is equal to delta G standard plus RT ln Q. So delta G standard is at a specific circumstances, but RT ln Q makes up for adjusting for what we're really at. We're adjusting the delta G to where we're actually at. What? So if you ever get as far as looking at physical chemistry is taking our standard values and adjusting them to reality. We tweak it for temperature, we tweak it for pressure, we tweak it for every little bit of reality. We're doing that a little bit right here, where we're taking our delta G standard, which is easy to calculate, and tweaking it for what is the actual concentrations we have at any given time. So, but with that in mind, we know that as Q approaches K, delta G non-standard approaches 0. So we get the magical equation that simplifies to delta G non-standard standard plus RT ln K equals 0, which is going to give us this final equation. That if we know delta G standard, which is the delta G you can calculate from using your book, we can figure out the K. If we know the K, we can get the delta G, one or the other. And so you could look at, because we can calculate delta G at various temperatures, we could say, what happens to K when I increase the temperature by 100? Well, I can calculate my delta G, plug it in, and change my temperature to reflect that and calculate my K. Did the K go up? Did it go down? And by how much? And so that's the last 2 slides of this chapter. We're looking at actually doing that. So calculate the delta G non-standard for this reaction at 25 degrees, assuming instead of 1, 1, and 1, we have 3, 1, and 2. So first things first, we have to calculate, well, we're given the delta G standard. So our equation is this. Delta G standard, which is what I'm calculating, is equal to 33.9 kilojoules plus R, which is 8.314 joules per mole Kelvin. Temperature at 25 degrees is 298 Kelvin, and then ln Q. Now Q, here's where we got to remember. Q is equal to, in this case QP is equal to pressure of products over the pressure of reactants, all raised to the respective coefficients. So ammonia is squared, hydrogen is cubed, nitrogen is to the first power, based on the chemical reaction we have up there. So with that in mind, respectively, 3 hydrogens, cubed, 1 nitrogen, and 2 ammonias. Now, if this was delta G standard, this number would be 1, 1, and 1. But because we're doing an actual real-world situation, this is not going to, QP is not going to be 1. So this is going to be, what, 4 over 27. And you should be able to at least, you don't necessarily know what that math is, but you should recognize that is definitely less than 1. 0.148. I'm going ahead and rounding that. 0.148. So I'm going to take the natural log of 0.148 to get my ln QP. That gives me a negative 1.91. Negative 1.91. We multiply that by my temperature, 298. We multiply that by my R, which is 8.314. You get negative 4733, which is, oh, that's a huge change, but that's 4733 joules. 4733 joules divided by 1,000 to get this in kilojoules, so negative 4.7 kilojoules. So we get negative 33.9 minus 4.7.
You multiplied your negative 1.91 by your temperature, correct?
And by my R. Yes.
You multiply it by your R?
Yeah, it's R times T times ln Q. The negative 1.91 is my ln Q. So this may seem like a piddly change, And in fact, it is. It's not a huge change. But it's not like we have zero amounts of ammonia. It's not like we have zero amounts of ammonia. We have a significant amount of ammonia already. But the big change is that, well, we have a lot more hydrogen than what Gibbs standard would predict. We have triple the amount of hydrogen that Gibbs standard would expect us to have, meaning it is more spontaneous by almost 5 kilojoules when I increase the amount of hydrogen like that. And in fact, if there was only one ammonia, or even less than one ammonia, let's say hypothetically almost zero ammonia. Almost zero ammonia means it's going to be a heck of a lot more spontaneous. Because as ammonia approaches zero, Q is going to approach infinity. Q is going to approach zero. And ln of zero is going to approach infinity. So as Q approaches zero, because ammonia approaches zero, essentially this is going to be infinitely spontaneous. But of course, the second we start to form any ammonia, it's going to slowly drop off. So it's just a process. Okay. So I'm just plugging my numbers in. The hard part is you have to remember, how do I set up my Q? How do I set up my K expression? Now, it's supposed to be tricky. It's just a refresher on chapter 15. Okay. For this reaction, calculate delta G standard for the following reaction, and what is the equilibrium constant at 298. So the ozone decomposition reaction. So first, let's calculate delta G. Delta G is products minus reactants. So products, the standard for this is 0. Pulling them right from there. And we have oxygen is 230.1. And ozone is 163.4. These guys are non-spontaneous to form. These guys take energy to form. These guys are not particularly stable. So what does that mean? This reaction is spontaneous by negative 393.5 kilojoules. Now, what would the equilibrium be for this guy? So delta G is negative 393 kilojoules. So this is the hard part. You have to watch your units. This is kilojoules per mole. So how do you solve for K? You have to get ln K by itself first. So I'm going to divide by negative R and negative T. This is where you want to be careful so that our units stay there. The negative 393.5 kilojoules per mole. Well, R is in joules per mole. So we want to say, well, there's 1,000 joules in 1 kilojoule times 1 over negative 8.314 joules per mole Kelvin. Mole, kilojoules, kilojoules, joules, joules, times 1 over, what we said, 298 Kelvin. So Kelvin cancels out too. So what are the units we're left with? Well, conveniently, we're left with 0 units. Well, remember, what are the units of K? K doesn't have units. So we are perfectly all right there. So we divide our 393,500 by 8, negative 8.314 divided by 298. You get this whole left side is equal to 158.8. Now, how do we get K? We're going to have to take the inverse natural log. The inverse log, for our log, we said the inverse log is 10 to the power. With inverse natural log is that e to the power. So we're going to take e to the power of 158.8. And you get, holy shit, a number that almost blows your calculator out of the water. You get K is equal to 9.2425 times 10 to the 68th power. This is incredibly product favored. This is incredibly spontaneous. And these really spontaneous reactions will be incredibly product favored. These incredibly spontaneous reactions will be incredibly product favored. In fact, if it gets too much higher, it can make your calculator go overflow and it just stops calculating it. But thankfully, this is the Gibbs standard doesn't actually occur in nature. Because for this to occur in nature, you would have to have 1 atmosphere of oxygen, 1 atmosphere of ozone, and 1 atmosphere of monoatomic oxygen. Now, based on what we just saw that last slide, when the reactants are larger than the products, it becomes more spontaneous. Based on the fact we have a shit ton of oxygen for us to breathe, and we're not choking on ozone all the time, the amount of ozone and amount of molecular oxygen are a lot less abundant. And because they're a lot less abundant, this makes this reaction a lot less spontaneous than it may appear to be. Because the Gibbs standard is hypothetical, the Gibbs non-standard is what we are physically seeing. So this is not destroying all the ozone in an instant, because we don't have ozone in that kind of concentrations. But so the K for the real situation might be a lot. I mean, the K is still what it is, but the Q is going to be a lot smaller. So the reaction has a lot less shifting to do. So I'm going to go ahead and clear this. And this is the end of this chapter. So just a quick reminder. What did we have? What reactions did we have? We learned we learned about S. We learned how to calculate L. That's the delta S of reaction is equal to the sum of the S of the products minus the sum of the S reactants. We learned delta S surroundings is equal to negative delta H over T. And we learned that from the second law of thermodynamics, the delta S universe is equal to delta S system, or delta S reaction, plus delta S surroundings. I've run out of room. So that was the, oh, for God's sake. And now, let's see if I can, I'm drawing on my wall. Okay, that was the first thing we learned. Then we learned about Gibbs, that delta G. And we learned about how we can calculate Gibbs either delta H minus T delta S, or we can do also equal just the sum of Gibbs products minus sum of Gibbs reactants. The same way we can calculate delta S. We learned when delta G is equal to 0 at equilibrium. And we learned to calculate that equilibrium point, we can say delta H or delta S is the T when G is 0. And then finally, we learned our last two equations. Delta G equals delta G naught plus RT ln Q. And we learned delta G naught equals negative RT ln K. These are our reactions. This guy is simply a rearrangement of this guy. These guys are essentially the same things. We learned this is probably the hardest part of this chapter, but I hope it's not too hard. I hope it's not too extreme, too intense. But that is this chapter. There's a few new equations.
Can we walk through another one of the Gibbs one?
Sure. Let's see. Of the bottom one.
Yes, sir.
Okay. Let's see. Close this out. Stop share real quick. I'm gonna open up Achieve. Okay, let's see. See how long it takes me to get into Achieve. Easiest way to do this would be okay. Don't forget, Achieve still exists. Be working on that. I don't think we might do homework. Yeah, we still got homework 18 and 19. But okay, course plan. There should be at least one or two of the okay, homework 18. It's not due for a long while, at least for 18 and 19. Let's see. Okay, here we go. States. There. Let's see if this is okay. This one is it's number 11, so okay, number 11, saying if this is my delta G for this reaction, what is our K at 298? That's my alarm, so I'm going to do this question and in this episode and restart it in a minute. So, but let's do this question first. Oh, sorry, I got a screen share again. Okay, share. Okay, there you go. This is number 11 in chapter 18 homework. Now that you can actually see this. So a generic reaction A plus B goes to C and D. That part doesn't matter. Delta G is 18. Delta G standard is 18.08. It's at 298. So the reaction is delta G standard equals negative RT ln K. If you're not trying to find a concentration of any of these products or reactants, you don't need the actual equation. So they give us the delta G is 18.08. It's in kilojoules. So the first thing I almost always do is convert either kilojoules to joules or joules to kilojoules. So I have 18.080 equals negative RT ln K. Second thing I do, I divide by negative R and negative T. So dividing 1808 by, so R and T, so 298 and 8.314 together make up negative 2477.572. So I divide that by,
What's the R?
R is the ideal gas constant,
Negative
8.314.
8.314.
It's a modification of the one, you might be familiar with this guy, 0.08314 bar liters per mole Kelvin. Well, a bar liter is equal to a joule. 100 bar liters are in a joule. So I'm just converting this guy to joules by moving that guy, the decimal, 2 places over. But so I did this math. And I get negative 7.297 equals ln K. And then finally I inverse log both sides. Make sure you have the right sign or you're going to have a very different K. So I do this, inverse log of that, inverse log of that. And what I get is 6.77 times 10 to the negative 4th equals my K. .77 times 10 to the negative 4th equals my K. So that right there is the answer for this one. So they didn't put it in scientific notation, but it's, you know, 3 zeros and a 6 7. And they rounded up. Don't know why.
Dr. Evans, I'm getting an error when I try to do my negative log.
Not negative log, inverse log.
Oh, okay.
Inverse, so inverse natural log. So the second ln. So you'll probably hit the second button, function button on your calculator, followed by the natural log function on your calculator, and that will give you that e exponential. And
It looks like it with E with like an expo.
E raised to the power of x is what it looks like.
Okay.
So try that. We'll finish
I got
up.
it now.
You got it now?
Yeah, thank you.
Okay, so yeah, just make sure we know our calculators, because
Noob.
yeah, this E, the cap, oh, I got rid of the annotation, but this E in the calculator does not equal this E, because that is a constant. That guy is that E is 2.718. It's like a constant, like pi. Pi is we all know 3.14 or something close to that. Well, E is another magical constant. And so it's just, I don't really know, I'd have to remind myself why exactly natural log is oftentimes better and more useful, but it just like, yeah, it does make the math work out really well a lot of times. Okay, so I'm going to go ahead and stop this. I'll end this, and we will. Okay, so let's go back and do the next problem. Let's see. No, not the next problem. I lied.
Is there one like we have to set up a queue or something?
Yeah, let's see. That's probably. Okay. Let's see. If. Okay, not that one. That's close to being like that. Okay, here we go. So for this, what is it? Okay. Oh no. Okay, this one's close. That I'll go ahead and do this one. This is not a Q1, but it is a turning K into delta G. It is a working backwards of the one we just did. This one is, I give you the equilibrium concentrations of each reactant and product, and then you find delta G standard at that temperature. So last time we had delta G and we're finding Q. Now we have all we need to find Q or K, and we need to find delta G. So for this reaction, 3A plus 4B goes to 2C and 3D. Our K expression is going to be D cubed times C squared over B to the fourth, 8 times A to the third.
And it's just products over reactants.
Products over reactants. It's just every bit of Q or K or all the equilibrium stuff we've been doing for the last
Wow.
like couple months. So 5.83 cubed, 4.55 squared over 5.15 cubed and 5.80 to the fourth. So just got to make sure you have this typed into your calculator right. Make sure you include whatever parentheses you need to make this work out. If you don't have the right parentheses or you're not getting this number, check how you're putting it in and make sure you're not making silly errors. Remember, you may know what you want, but your calculator doesn't always know what you want. Okay. So mine, I'm getting K is equal to 0.0265. We'll go one more digit, 4. 2654. So that is our K. With that in mind, ln of 0.02654 is, now I'm just going to do a second answer. I'm not going to do the whole rounding, so this might change a little bit for you. That is equal to negative 3.629. That is that whole thing. Now I'm plugging that into here. So we have to just keep evaluating. So that whole thing is times 298. That whole thing is times negative 8.314. So times 298 times negative 8.314. So delta G. So doing that, I get 8991. However, units. There's kilojoules. This guy's in joules. So we have to divide by 1,000. The correct answer is positive 8.9. 8.99. So
I did not get that. I messed up.
what did you get?
I got 9.74.
9.74. Okay. Now, so what did you get for your LNK?
LN, I got I got the same that you got, 0.02654.
Okay,
And I
you
did
took the
ln
natural log of it.
0.02654.
Yeah.
And I got negative 3.629.
Okay.
And then I multiplied that by my t, which is 223, right? Just 25 plus 298.
No, that's the problem. 25 plus 273. You get 298.
I used the wrong.
Yeah,
Two,
that would be it.
Whoops.
That would be it. So,
Whoops.
yeah, well, we all make mistakes. But that's why I work out, show all my work so I can know where I screwed up when I screw up. I'm like, oh, I skipped this step. Oh, I didn't convert that. Now, I may not be showing all the work as I annotate sloppily onto this computer screen because I do run out of room, sadly. But so we're just working from this. So, I mean, there is some problems like this. Let's see. Just looking at some more problems on this. Okay, this guy would be your what's your Gibbs non-standard? They give you the Gibbs standard, and they give you the pressures of these guys during the reaction. We'll do this one. We'll finish up with this guy, which is, oh God, what? Is this the last one? No, but okay. Yeah, its number's like 16 on the thing. We'll finish up with this one and then move on. So with this one, they give us delta G. They give us our concentration. So we have to find out first what is Q. Q is equal to products over reactants. So I'm going to go ahead and just put in the numbers 0.950 squared because we have 2. O2 is 0.150 and 0.250 squared because of, so our Q. So first thing off, I almost always find my Q. I mean, you could plug them all into one big equation and you would probably be fine, but I almost always find my Q separately, just to force a habit. So Q is 96.26. So delta G equals delta G standard plus RT ln Q. Watch out for the sign. This guy, the last equation was a minus. This guy's a plus.
How do you know is this the one you're supposed to use? You're supposed to use this one because they give you they
don't say it's at equilibrium and they ask for the non-standard.
Okay.
They ask for the non-standard. So the last guy, I'll go back to the last guy in a second. But the last guy, I'm pretty sure they said, here is the concentrations at equilibrium. And this one say, what is our delta G for the reaction when this is the situation? So it's nothing about equilibrium. It's like, it just says when we're at here. So RT ln Q, I'm going to do that whole thing as one part. 8.314 times 298 divided by 1,000 times ln of 96.26. So
can we go ahead and change the R to kilojoules since we do that?
That's what I just did.
Oh, okay.
Yeah, that's what I'm writing out my work. 96.26. That whole thing goes to 11.31, and well, this is added on to my delta G standard. The delta G standard is negative 69. All right. So delta G plus all that junk gives us the delta G standard, delta G non-standard, which is our delta G at our current situation. So I get negative 57.7 as my answer. So that's why I'm doing this in parts. 7.7. I'm doing this in parts so that I can see exactly where this, I can like, oh, check each number in turn. So if I plugged in 57.7 now, it's wrong. First thing I would do is I would check these numbers. Does this give me 57.7? Do these numbers look right? Well, does this number look right? Yes, they add up to 57.7. Then I'm like, okay, does all this number look right? Does this times that divided by 1,000 give us 11? Yes. Okay. Well, then obviously they screw up there. Then I look, is this set up properly, and does this give me 96? If it does, then oof, I'm in trouble. But if it doesn't, if I can obviously see an error in this step or this step or this last step, then I can quickly figure out where I screwed up. Okay.
Can I ask a question?
Yes.
Okay, so I got to the point where I divide everything by 1,000, and I have different numbers, but I have 17.61. Where do I need to go after that step?
17.61. Okay. Then you add that to this. Essentially, when you divide all this by 1,000, you're getting the modification term, what takes the standard to the non-standard. And so
Okay.
you're just saying, so all this is your RTLNQ. All this is your RTLNQ. And you're
Okay.
just, at this point, you're just adding that to this. So the last step is just you're adding two numbers together.
Okay.
So I just want to jump back for a second so we can see. So notice on this one, we said that, what is the standard Gibbs? Okay, the equilibrium, the partial pressures were found to be this. So it's telling you these are equilibrium partial pressures. So it's telling you it's at equilibrium. What is the Gibbs free energy? What is the standard Gibbs free energy?
So if we see equilibrium, we go straight to the Gibbs standard.
Basically, yeah, you'll see either terms equilibrium or standard. It's asking for standard. It gives you equilibrium concentrations. Those two words, one of those two words will be used. Now this guy, going back to this guy again, they give you the Gibbs. They don't say the Gibbs, they don't say the standard Gibbs. They say what is just the Gibbs with no knot reaction with, and they don't make reference to the fact it's at equilibrium. So okay, well that's where we're gonna. So okay, let's go back to starting the chapter 19, which is the last one we'll have on the exam 4. We'll do the thermodynamics and electrochemistry.
I like the joke. He said he felt thoroughly drained, so they charged him. Dang, I just broke my pencil.
Okay.
What? Just broke my pencil.
Okay. Okay. So we kind of saw these before when we looked at aqueous chemistry.
Oxidation.
So we're doing a redox reaction. So, but we're going to hit them way more in depth this time around. What is the big thing here is we're going to see electron transfer in all of these reactions. Just like when we had acid base, if you have an acid, you have to have a base to be acid base. If you have electron transfer, you have to have an oxidant and a reductant. You have to have one guy losing the electrons and one guy gaining the electrons. Now, they could be the same guy, but there's going to be someone accepting it and someone losing it. So, is it electron transfer? So the oxidation number, so the charge of that element will change. You can't have one without another. So if you're clever enough and you can see one element changing, there must be a second one in there somewhere. Now, an oxidation, as a quick reminder, is the loss of electrons. It's the oil from oil rig. Oxidation is loss of electrons. When you lose something that is negative, you become more positive. In terms of organic chemistry or the chemistry of life, when something is oxidized, it gains more oxygens. Like ammonia, NH3 is the least oxidized version of nitrogen. Nitro group or NO3 or nitrate would be the most oxidized form of nitrogen, because that has 3 oxygens associated with it. Carbon dioxide is the most oxidized version of carbon. Methane is the least oxidized. So you're also going to see, usually when you see an oxidation, if you're talking about in terms of oxygen, you're going to see a loss of hydrogens as well. Because you got to say methane, 4 hydrogens bound to carbons, to 1 carbon. First, carbon dioxide, no hydrogens bound to carbon, and 2 carbon-oxygen double bonds. So 4 bonds between the carbon and oxygen. And so we can have various degrees of bonding in between that, like an alcohol, which is 1 carbon-oxygen bond, an aldehyde, which is, or a ketone, which is a carbon-oxygen double bond, an acid, which would be a carbon-oxygen double bond and a carbon-oxygen single bond. And then, of course, carbon dioxide. Now, reduction is just the opposite of that. You're gaining electrons, thus you have to become more negative as you do that. And in terms of organic chemistry, again, you're losing the oxygen. You're gaining some hydrogen back. So reduction is gaining electrons. Oil rig. Or you might have heard of Leo says Gur. You have the line, losing electrons is oxidation, gaining electrons is reduction. However you want to keep it straight in your mind, you got to keep it straight. Okay, so got to remember these simple rules. This will help us a lot. The rest of it has to be context. Any pure element in its standard state without a charge is 0. Any oxygen within a compound is almost always -2. Any hydrogen in a compound is usually +1. Almost everything else can be determined by context. So looking at this, 2 zinc solid, 1 zinc in its standard state, plus oxygen gas, well, oxygen in its pure elemental standard state goes to 2 zinc oxide, a compound. Well, pure element is 0. Oxygen, pure element, 0. Oxygen's in a compound, it's probably -2, which means this zinc has to be +2, because for a neutral compound, all the positives and negatives have to add up to cancel out. So zinc starts at 0 and goes to +2. Because it's starting 0 and becoming more positive, it's losing electrons. Because a positive plus a negative cancel out. So it's losing electrons, so it must be oxidized. Oxygen starts at 0, goes to -2. Well, it's being reduced. So reduction. Oh, crap. This is weird. So now here's where it gets a little tricky. Verbiage can be a little messy here, but because of the nature of this, we have the oxidation pair. If something is oxidized, it is reducing something else. So oftentimes we refer to that as a reducing agent. A reducing agent, because it's reducing something else as it itself is becoming oxidized. Now the oxygen is being reduced, so it's an oxidizing agent or an oxidant. So it's kind of like saying, kind of thinking how the fact that as an acid donates a proton, it acidifies something else, thus becoming a base. And a base becomes acidified, thus becoming an acid. The idea that zinc, because it's oxidized, it is reducing something else. And oxygen, while it's being reduced, it is in turn oxidizing something else. And I'll go ahead and stop after this slide, but the last thing I want to leave you with, sometimes you have these weird situations where the same thing is oxidized and reduced. This is called disproportion Asian, where this breaks into two different compounds. And this is the naturally occurring situation that occurs within hydrogen peroxide. We have stabilizers in there to keep it from, to slow this down, but this does happen over time. So hydrogen peroxide will expire. And it's not bad, it's not going to poison you, it's just not going to be effective. Because hydrogen peroxide, this is one of the few times where oxygen isn't -2. And it can't be. Because if you look at this, 2 oxygens, each -2, would be -4. Then hydrogen, each one being +1, would make this whole overall thing -2. But so in order for these guys to cancel out, hydrogen at +1, oxygen has to be -1. So what we see is 2 oxygens going from -1 to -2, and 2 oxygens going from -1 to 0. So 2 oxygens being oxidized, 2 oxygens being reduced as that breaks apart. And that is a naturally occurring process. So I'm sorry we didn't get into any clicker questions today, but that is where I'll leave you, because the next step will be balancing these guys and trying to learn how to properly balance these equations. And I don't want to get into that. That's a whole mess. So for everyone else, thank you for showing up. If you want to make sure you don't miss any videos, please subscribe, like if you want, if not, whatever.